Hello everyone, and welcome to this class on actuators in the course of Mobile Intelligent Robotics. As in most cases, when we talk about robotics, actuators is a very large area which could bring us down into a lot of details. So we will have this class looking into the main aspects of this part of any intelligent mobile robots. And basically we will classify the kind of actuators according to different characteristics, and we'll give an overview of this field. Okay, if we'd like to give a general definition or a broad definition of an actuator, we could say that an actuator is an active device. This is particularly important in the sense that it converts a primary source of energy into some sort of physical movement, or sometimes also into some sort of force exerted upon a certain device. Given this broad definition, we can generally classify the actuators considering, namely, first, the type of primary energy which is used to generate motion in the actuator. It is important in this case to stress that this primary energy source is a primary energy source that actually is used to generate a motion, which means that we could have another source of primary energy which in turn produces this primary energy. For example, if you consider an electrical motor, the primary energy that we're talking about is electricity, of course, but on the other side, this electricity can be generated by, for instance, an internal combustion engine. The second type of definitions that can generally classify an actuator is the type of generated movement. So we look into generators according to these two classes. For each of these above types in terms of classification, we could also, or it is also possible to classify actuators according to the type of technology used by the actuator, which is basically the physical principle of energy transformation into physical movement. There is a note also that some devices, when we talk about actuators in general in robotics, which normally I classify as distinct actuators, may actually be a more sophisticated version of a simple actuator. For instance, we can consider the actuator itself integrated with a control system, in this case the electronic control system, responsible for the actuation level. So what we will start to do in terms of classification of actuators is to look into the type of primary energy that is used to generate movement of the actuator. And the first one that we will refer is the electrical primary energy. In this case, the electrical actuators transfer primary electrical energy, normally stored in batteries, for instance, sometimes rechargeable, into the intended movement. As we will see later, there are different technologies depending on the characteristics of the actuator that we are considering, and also depending on the specific application for which the actuator is used. In mobile robotics specifically, electrical actuators represent maybe the larger and main class of actuators due to its diversity and ease of adaptation to every type of applications. For instance, in the work that you have done in the practical part of this course, using the micro-rato environment, we consider two devices that are responsible for the movement. In this case, two electrical motors that have two wheels attached to them, and it's by controlling these electrical motors that we can actually move the robot around, for instance, a maze. These are two images. We could have thousands of different images of this type of examples of small electrical DC motors. If we are talking about small robots, normally we will have DC motors within powers that can range from some sub-watt power level to some 100-watt level. But if you move into larger mobile robots, which is, for instance, the case of autonomous mobile driving cars, then we may have DC motors or electrical motors that are able to deploy energies in the level of hundreds of or thousands of watts in this case. The second type of actuators, according to the type of primary energy, are the pneumatic actuators. In this case, we are talking about actuators that are powered by energy which is stored as compressed air or some form of compressed gas. And these actuators are used in situations where we want an accurate and easy to control movement for this particular application, but that in turn requires a force which is not a critical criteria. This is because basically any gas can be easily compressed, and being compressible, it means that you cannot ensure that the force that you are exerting is enough for the application that you are applying this type of actuators. Of course, this type of actuators require very high pressures and therefore extremely robust and heavy containers. Otherwise, you are not able to actuate upon these devices. They are generally less efficient in converting energy than electrical solutions, which means that the percentage of energy that you can actually transform into work is less than electrical actuators and is therefore less common in mobile robot applications. On the other hand, you can find a lot of this type of pneumatic actuators in industrial control applications. A possible example of pneumatic actuators are pneumatic pistons, and this image can reveal some sort of devices such as this. Using pneumatic devices, we can also imply actually, or not imply, but use and develop solutions that can include, for instance, logical solutions, which means that we can use pneumatic actuators that can be used as an AND or a NOR device, so that we can in hardware implement, using these solutions, logical solutions. The third and last type of actuators, according to type of primary energy that we want to consider, are the hydraulic actuators. In this case, instead of a gas, we use the flow and pressure of a fluid to convert the primary energy into linear and or rotational motion or torque. These kind of actuators are used only in situations where the force required is extremely high. Since we are using a fluid, not a gas, a fluid is not compressible, which means that we can actually exert very, very high forces using this kind of actuators. Also, it is true that they require heavy and bulky mechanical structures, which means that they normally are not used in small robots. They can be used in very large and heavy-duty robots. Typically, they are found in large machines, such as autonomous mobile robots working in mines, for instance. And within this particular course, we could say that hydraulic actuators is not considered the most relevant type of actuator. On this image, you can see this monster truck, which is actually a robot that works in open mines in Australia, which means that they are not driven by a human pilot. They are completely autonomous and move around the mines on themselves, and they only require a single person in the central room to verify that everything is going on. Of course, this person can overrule any decision of this device, which is a huge, we don't have here actually something to compare in terms of height, but I could say that probably one of these wheels is taller than any person. So this is a type of an autonomous mobile robot, which is very, very huge and is only used in very, very specific applications. So another example is here. This is a pneumatic linear actuator, which means that it produces linear movements using a fluid to convert this primary energy into the linear movement itself. On the other hand, we also said that we can classify actuators according to the type of generated movement produced by the actuators, and here we can consider basically two types of movements. Rotary movement, which means that the primary energy is converted into a rotation motion, which in turn may be continuous, which is, for instance, the example or the case of the robots in the micro mouse micro hat environment. It can be a positional movement or a source of application of force, which means that it doesn't actually moves, but it produces a torque upon a certain device. There is also actuators which produce a linear movement. So linear motion is the target of this kind of actuators, and the purpose of this movement can also include the direct application of a force, as the case of the rotary ones, the position of a mechanical element, or the execution of a continuous repetitive motion, which is normally designated by reciprocating system. A piston in an engine motor, for instance, is an example of a continuous repetitive motion, so a reciprocating system. Some notes that we can add here. First one, when the objective is the direct application of a force, which is one of the possible applications, it is common to find solutions where the primary energy applied to the actuator is partially stored in a mechanical device, which means that we can also use passive devices, for instance, springs, that can absorb energy and then uh, let it out when it is necessary. So, for instance, in the case of a spring, you can apply a force. The spring will absorb the energy, normally reducing its length, and then when released, it can restore the original configuration when the primary energy source is removed. And passive energy storage elements can also adjust target positions based on external forces. And this last sentence means basic that we have or can consider two types of actuators. One type that we call compliant actuators, which means that the actual force that is exerted is somehow limited, so that if there is a counter force that opposes a movement, the actuator won't force above a certain level. And these actuators are opposed to what we call the stiff actuators, that will apply the maximum possible force to ensure that the final position is reached. In some cases, we also stated that before, the very primary energy source of any of the energy sources that we have considered, electric, pneumatic, and or hydraulic, can in fact be a different nature, particularly when the required power is very significant. For instance, when we saw that very large truck used in open mines in Australia, the original primary energy source is an internal combustion engine based on fuel. So the very, very primary energy source is the fuel itself, which is then used to, through some pumps, generate hydraulic forces. One example of what is stated above is the use of an internal combustion engine, as I just said, to derive from the combustion of hydrocarbons and turn it into electrical, pneumatic, or hydraulic energy. A good example of hydrocarbons as primary source of energy, as we just talked about in the previous slide, is a well-known robot called Big Dog by Boston Dynamics. And probably most of you already heard about Boston Dynamics. There are a lot of very interesting mobile robots, normally using not wheels but legs, developed by Boston Dynamics, some of them resembling humans. But the Big Dog, for instance, is powered by a two-stroke, one-cylinder, 15 horsepower Go-Kart engine. So it's an internal combustion engine, and basically this engine operates at over 9,000 RPMs, and in turn the engine drives an hydraulic pump, which in turn drives the hydraulic leg actuators. So we could say that there are two levels of primary energy source. The top level, which is the fuel, and the second level, which is an hydraulic energy source. Each leg in this case has 4 different types of actuators, and each actuator unit consists of an hydraulic cylinder, a servo valve, a position sensor, and a force sensor. So this is an integrated actuator that already has sensors, which is a theme that we already heard about previously. So the integration of actuator and sensors together with electronics to control the actuator is the most common way to see an actuator. Just as a matter of curiosity, in the case of the Big Dog, what they do is to somehow replicate an animal leg in each of the legs of the Big Dog. This is the example of an animal leg, such as dog, for instance. And we have a series of joints, and together with the joints there are some muscles that are responsible for different levels of actuation. For instance, this top one is only responsible for actuation, so it exerts force basically. Then at this level there is a mix of compliance and actuation. The compliance is a part where you have these passive parts that can absorb and release energy together with actuation. And then the third level, close to the floor, is responsible both to compliance and dissipation of energy. And so this dissipation of energy is the way to ensure that when an animal is running, for instance, and strokes the floor, does not break a leg in this sense. If we look into the Big Dog solution, they also have the actuation level on the top part of the leg. Then you have compliance and actuation, so there are springs and hydraulic, in this case there are hydraulic actuators. And there is also the dissipation part on the bottom, which is basically a rubber that can deform under pressure and release the energy in the form of heat. So they actually follow a very similar solution to the one that are present in the leg of any animal. This slide, you can see an example of the Big Dog, and namely the level of control that is required to ensure that it does not fall on the ground. And it's amazing what they can actually do with this kind of devices. The Gokart engine is on the top over here. Maybe you could hear the noise of it running. It's running at 9,000 RPMs, and it's generating the hydraulic forces required to drive the legs. As you can see, it can walk on stones, over snow, even on ice, which is a really interesting situation. You can see it now, and it's amazing. You can see that it won't fall, it will adapt and absorb all the energies that try to make it go down to the floor. Even the knees sometimes are used as a compliant actuator to absorb this energy. On the top you can see the Gokart engine that drives these particular robots. has a payload of 340 pounds, so around 120 kilograms. It has been proposed to be used by the US Army and has been refused simply by the fact that it produces too much noise. So it would be easily detected by an enemy, let's so call it, because of that level of noise. So moving on, we'll now look into the rotary actuators, and the most common rotary actuators used in autonomous mobile robots, if we exclude, of course, the very large robots, use electricity as its primary source of energy. These actuators are commonly referred as drivers or motors, depending on the application in which they are included. And because they are so essential components in the mechanism of the locomotion of robots, they may in turn be of various types regarding the way the electrical energy is transformed into mechanical energy. That is to say that there are different types of technology with different costs, of course, different performances in terms of efficiency, that can be used for drivers or motors. These are very relevant within, as I said, within the intelligent mobile robotics. And according to this technological side, we could consider at least three types that should be highlighted. The first one, which is very common, normally it's the less expensive one, is the brushed DC motors. We'll talk a little bit about this in the next slides. Also, there are the brushless DC motors, and finally the stepper motors. So in the next slides, we'll go through these three types of motors and compare some of their main characteristics. Before going into the specifics of the brushed, brushless, and stepper motors, there is a few items that we could refer. It's not really relevant that you know exactly all of them, but it is important to understand that according to the application, an engineer should look into all these characteristics of an electrical motor so that can choose the optimal or quasi-optimal solution for the particular application. In general, these characteristics of the motor are the ones that are relevant for the final selection of the motor. Some of the most important parameters that normally we have to consider are this list that we have here. Nominal supply voltage. It depends on the type of energy source that you use. They can range from 3 to 48 volts. These are, of course, indicative figures for mobile robotic applications. The torque response as a function of rotation speed, so which is the force that make the wheel turn. These are defined in Newton meter by minute. And the stall torque in Newton meter, which means the torque that must be exerted to stop the motor to rotate. The range can go from millinewton meter to hundreds of Newton meter. Steady duty maximum torque, which is the maximum torque that are normally used in steady duty. Typical current typical current at steady duty in ampere, from milliamps to 100 amps. Nominal angular velocity with no load. That is when there is no load, so the rotor is rotating freely. And also the nominal angular velocity in steady duty. That is when there is a weight and a load applied to the motor. The ranges can go from, for instance, 0.1 RPMs to 50,000 RPMs. Normally, the nominal angular velocity go from 0.1 RPMs to 35,000 RPMs. Also, the nominal power, expressed in watts, can range from milliwatts to hundreds of watts, for the kind of applications that results in robots that can be used inside the house, let's say. Apart from the parameters we considered in the previous slide, sorry, we may also consider, depending on the application, other parameters such as the start current. Normally, the startup current is the maximum current. It's when we develop the maximum force also. The peak current, mechanical time constant, which is something that has to do or may have to do with the inertia of the motor, the rotary inertia itself, the motor volume, it is important in terms of the mechanical design of the robot, and finally the weight expressed in kilograms. So you have motors that can weigh less than a gram, maybe, depending. There are some micro motors up to tens of kilograms for typical applications of the type that we are considering. Depending on the technology, we can also need to consider, or may also need to consider, other parameters such as the efficiency. Efficiency is basically the percentage of the primary energy that is actually transformed into work. The difference between this efficiency and 100% is normally dissipated as heat. The number of poles of the motor, magnetic characteristics of the rotor and or the starter of the motor, mechanical rotor configurations. As we will see later, there are what we call in-runner motors and out-runner motors, and also maybe the geometry of the motors. A good example is the planar motors that are used, for instance, in electrical bicycles. And we also, I think, will look into something similar to that. So let's start by looking now into the brushed DC motors. In the version shown here in this image, there are only two poles. Two poles are not enough to ensure that the motor will start. So normally these brushed DC motors will have at least the minimum of 3 poles, but to demonstrate the principle, this is good enough. These poles are what we consider the stator. So this is non-moving parts of the motor. They are permanent magnets. This one is the North Pole magnet and the South Pole magnet. And then you have the rotor, which is this inside part that include, in this case, two coils, the one on this left and the one on the right. And these are wound around ferromagnetic armatures, and when these coils are traversed by a current, they generate a magnetic field that, in conjunction with the permanent magnets, tends to generate a rotational force in order to align the magnetic fields generated in the rotor. So looking a little bit into the details, one of the reasons why this is called brushed DC motors is that the current that flows around these coils are based on the voltage that is applied to these two electrical connectors, which is basically copper. They are independent. One of these copper parts is connected to the top coil, the other is connected to the bottom coil. So in this configuration, the positive part of the voltage is being applied on one side of this coil and will move in this direction. So this will generate a magnetic field that will attract this part into the North Pole. The other coil is transversed by a current which is generated by the opposite direction. So they will go through the minus part and circulate into the positive part of the voltage, and therefore will generate a magnetic field that will attract this part or this bottom coil to the south pole, generating a rotation movement. So the reason why these keep rotating when there is in this case voltage applied in these 2 points is because These 2 points is rotating and are switching the connection of these two coils into the voltage applied. So the switching of the current flow direction is performed mechanically by what we call the brushes. There is a mechanical contact here. This will wear over time, so this is one of the problems of this kind of solution, and this is also the reason why we call these motors brushed DC motors. In a simple version, as the one of the image, where we have only two poles, there is an initial balance point that cancels the forces. And this is the reason why this is not a practical motor. We would need at least three poles in order to ensure that the motor will work correctly every time. So this is an example of a rotating mover. As you can see, the brushes are static, but the connection of the brushes to the coils, which is performed on those copper parts, is rotating, and this ensures the switching and ensuring that the motor is rotating over and over and over again. One of the potentially interesting parts of the brushed DC motors is that the speed control of the DC motor can be easily done by varying the voltage applied to the terminals, which means that if you vary the voltage applied to the terminals, you are also changing the amount of energy that you provide to the motor, and therefore the velocity of the motor will change. In practice today, this is not done in this way, since most of the current controllers for the brushed DC motors are digital. And therefore, we are not changing linearly the voltage applied to the motor. So in the case of digital applications, what we do is to not change the applied voltage, but modulate the pulse width of a constant voltage. We call this a pulse width modulating controller. And in this way, basically what we do is to apply a signal, which is a square signal at a fixed frequency, and we change the amount of time regarding to the period during which the positive voltage is applied. For instance, in this case, we are applying just a small amount of energy, because during the period, most of the time, the switch is off. This is a very simple design that represents this principle. This is the Pwm Control with a switch. When you turn on the switch, you apply a voltage to the motor. When you turn it off, the voltage is removed. The time that the voltage is on in regard to the period is called the duty cycle. So in this case, we have a very small duty cycle corresponding to a very small energy provided to the motor. In this example, we have a 50% duty cycle, which corresponds roughly to 50% of the energy that you can provide to the motor. And in this case, you have, for instance, something similar to 90% duty cycle. Normally, you do not apply 100% duty cycle, because when you do that, you are no longer able to control the motor using, for instance, a PID controller. So normally, the maximum applied duty cycle will be around the 90%. One of the problems of the simple solution that we saw in the previous slide is that the motor will only rotate in one direction. And in some applications, this may not be a problem, because that's the intended direction, but it's quite common that a motor is attached to wheels so that we can move the rotor around, and in that situation, we may want to change the direction of rotation, of course, so that we can actually inverse the rotation regarding the normal rotation direction. And in that case, the polarity of the applied voltage must be reversed, which means that we have to find out a way to change the direction of the current in the motor so that it can rotate in one direction, clockwise or anti-clockwise. The normal solution is based on what we call the H-bridge circuit, which is simply designed in this picture here, and this will allow the full control of the motor, both in terms of speed and direction of rotation. Basically, the idea here, as you can see, there is not a single switch. These are, of course, electronic switches based on transistors, but we have 4 switches, and the motor is connected between point S1 and S2. So the concept is not very complicated. If we close the top switch on the left and the bottom switch on the right, then there will be a current flowing from this left side through the motor to the right side to the ground. If we change those 2 switches and close the top right switch and the bottom left switch, then the current will flow in the opposite direction through the motor down to the ground, and therefore will change the direction of rotation. You can see down here the control signals applied to the switches. The blue switches are the top left and bottom right. The red switches are the top right and bottom left. In this situation here, for instance, the ones that are on, closed, is the PWM1H, which is this one here, and the PWM2H, which is this one here. This means that the connection is made between Vmax and Vmax, so there is no difference of voltage and there is no current applied. During this period, the ones that are connected are the 2 on the bottom, so this one and this one. And in this situation, the motor is connected on both sides to the ground, and of course there is no current. In this situation, the motor is stopped, basically. In the center one, you can see that there is a period between these 2 green dashed lines in which you have PWM1H closed, so it's this one here, and also the PWM2L, which is this one here. So during 50% of the time, you are applying a current that flows in this direction, making the motor rotate in that particular direction. This is basically duty cycle of 50%. During the remaining of the time, the switches are connecting either both Vmax or both ground. By changing these signals, you can also change the direction of the current. For instance, in this case, you have a similar situation like this, so you are still rotating in the same direction, but the duty cycle in this case is 90%. 90% of the time, you will have this one on and this one also on, so there is a current rotating in these will correspond to the maximum rotation, basically, that we can apply to the motor. Now moving on into the brushless DC motors, you can see here a 3-pole solution of a brushless DC motor, BLDC, let's say. And in this case, if you remember previously, the stator, which is the non-moving parts, were permanent magnets. In this case, it is the rotor inside which uses permanent magnets. And the stator, which is round, is made of a set of poles composed of 2 coils. So you can consider the coils A, the coils B, and the coils C. And depending on the way you excite these coils, you generate a magnetic field. For instance, if you consider this particular situation and you excite the poles B, this will force, depending on assuming that the generated magnetic field is the correct one, this will try to force this rotating part to align with these 2 poles. When this reaches this point, we then turn off these 2 coils and turn on the C, and this will generate a force that will tend to align the rotating part to these coils. If we want to rotate in the opposite direction, basically we change the voltage applied to these pairs of coils. This configuration has the large advantage that it eliminates the need for a mechanical switching system. So there are no brushes. This is the reason that we call this brushless, meaning that the durability of this kind of motors is rather larger than of the brushed motors. Of course, there is a downside, and the downside is that the control of this motor requires an electronic system that generates the correct sequential switching of the poles in order to generate the necessary torque that produces the current rotation of the motor. And the problem is that depending on the speed of rotation, also the speed of changing or switching the coils must accompany that. So it implies that there must be some sort of measurement, some sort of feedback that allows the control system to know exactly when to turn on and turn off each of these groups of coils in order to keep the motor running. So one of the obvious advantages of brushless DC motors is the fact that it requires virtually no mechanical maintenance and exhibit greater efficiency when compared with the brushed one. And of course, these are two very important advantages. In contrast, to control this type of motor requires a much more complicated control solution, in particular because it requires a mechanism that can provide information on the absolute position of the rotor. For that, we can use all effect sensors, for instance, or control electrical motion force measurements. Also, just to let you know, the number of pairs of transistors should always be equal to 2 times the number of poles used. And you can find BLDC motors that go from 3 poles, this is a simple solution, up to maybe 12 poles or more. Mechanical configurations of BLDC solutions include both inner rotors, which is the one that we saw before. So the rotating part is the inside of the motor, and on the outside are the coils. But there are also outrunners, which is the case of this image here, in which the rotating part is in the outside of the motor and the fixed mechanical part is in the inside. This is typically the kind of motor used, for instance, in drones that you know so well. This is an example of a 800 watt outrunner that can go up to 9,000 RPMs. From the electrical point of view, the interconnection of the poles can also adopt both triangle and star configurations, and this will result in solutions that are able or best applied to different applications. Finally, let's just talk briefly about stepper motors, which is the third type of technology that you can find normally in electrical motors. In a stepper motor, there is a rotor that you can see here containing multiple magnets arranged on a central piece of iron. So the magnets are positioned on these triangle points that you can see here. And there is also a set of electrical coils disposed around the periphery. This is the non-rotating part. This is the rotating part. And these coils, when energized electrically, will generate a magnetic force that will force the teeth to align with the coil. What happens here is that there is a mechanical offset between the teeth and the teeth on the coils, so that if you energize sequentially each of the coils, you will force the rotor to rotate a little bit, basically is 1/4 of the distance between two teeth, in order to align it correctly. This solution, because they are slightly out of phase, normally results in a motor that is not designed to rotate at very high speeds, but that can in turn be easily positioned in a certain angle. So you can move the motor up to a certain point and then keep the coil energized, and it will stop there. And the control is very, very simple also, and you can also generate very precise rotation speeds using this kind of solution. Switching the current to the next coil, as you can see, you can rotate the motor. The fact is that this sequence of energizing that will produce the alignment can also produce small mechanical vibrations, because actually you are normally trying to move the rotors a little bit and then slightly stop it. So sometimes these kind of motors can exhibit, depending on the way you control it, can exhibit some very small mechanical vibrations. But this can be used and can be very interesting in applications that normally does not require very high forces, but require very high precision of positioning or very high precision speed rotation. As a summary of what we have been discussing in the previous slides, you can see this table that basically shows which are the plus and the minus of each type of uh, technology of electrical motors. In the case of the brushed DC motors, this is very cheap, so they are the cheapest motors. They are very simple to control. There are available a large power range, and so depending on the application, you can find solutions for basically any possible application. It is very simple to start up. This also has to do with the control part. On the other hand, there is mechanical wear out because of the fact that it uses a brushed solution. The efficiency is normally not as high as the other two available solutions, and there is also a minus point on the power versus volume, which means that for the same power that you can obtain in a brushless motor, for instance, you require a higher volume and normally also a higher weight. Looking into the brushless DC motors, the plus come from efficiency, large range of rotational speeds. You can have brushless DC motors running at high as 15,000 RPMs, for instance. No maintenance, basically it's maintenance free, and good power versus volume ratio. Also, this is a good solution for planar topologies. On the minus side, the price, which normally the price for the same characteristics will be higher than a brushed motor, the complex control and complex startup in particular, and or need for accurate position sensors. This is clearly not a good motor if you want an accurate position application. In the stepper motor side, the pluses, we have very precise motor, can be used in open loop. Basically, you don't need feedback. It's very good for planar topologies, very useful in positioning applications, and also from the maintenance point of view, there is basically no wear out, so it's very good. The compromise between complexity and control is considered to be reasonably good, but on the other hand, this is the most costly type of motors it can find. So from the price, there is two minus here. Also, the efficiency is very low when compared with both brushless and brushed motors, and there is a possibility of mechanical vibration, as we have referred in the previous slide. Apart from the electrical motors, there is also another type of electrical device that can be useful within the mobile robotics, and we'll give further on an example of that. These devices are called generally solenoids, and is typically built from a coil which is mounted around a movable plunger within an air gap. And this is exactly what you can see in the image that is presented here at the bottom. The plunger, which is this cylinder here that you can see here, normally consists either of a ferromagnetic material or sometimes a permanent magnet, which is the case of these images in particular, since you can see that the south pole is on the left and the north pole is on the right. Whenever you apply a current to the coil, This will generate a magnetic field, and this in turn creates a dipole that generates a force that tries to align the geometrical center of the plunger with the geometric center of the coil. So in this particular situation, whenever you apply this current, the plunger, which is on the left or onto the left of the center of the coil, will be moved in and aligned with this coil. In these particular situations, if you reverse the current, then the force or the magnetic field will be also reversed. In this particular case, the force will be repulsive instead of being attractive, which means that it will push the plunger out of the coil. This possibility of changing the current and changing the direction of the force is only possible if you use a permanent magnet plunger, but not in the case of a plunger which is made of ferromagnetic materials. In most cases, the solenoid starts from a position where the plunger is geometrically offset, which means it's not centered with the coil, and whenever you apply current, this plunger is rapidly attracted to the opposite direction, that is in the direction of the center of the coil. And in order to maintain the exerted force, that is, in order to not allow that a plunger moves into the position where there is no force at all, there is normally a mechanical lock which does not allow the plunger to reach the equilibrium point. You can see down here an example of a simple solenoid. The black part corresponds to the coil, which is wound around the center of the plunger. The plunger is this larger cylinder here, and whenever you apply the current, a force is exerted through the plunger, and it moves in, and then it's stopped before it reaches an equilibrium point. To reset initial conditions, normally what we do is to add up a spring. The spring will absorb energy when the plunger is pulled in, and whenever you release the current, then the spring will pull out again the plunger to its initial conditions. As we have referred just at the beginning of this class, sometimes you can find actuators that are called with a different name, but that are in fact a more complex set of more generalist and simple actuators. This is the case, for instance, of servo motors, and a servo motor is the name given to a combination of electrical DC motors. It can be either brushless or brushed, a reduction gearbox, and an electronic control loop. Servos are intended normally for applications of angular positioning, which require a good accuracy. So normally they are not designed to generate a permanent rotating movement, but rather to move an arm between two different angular positions. Here you can see a very simple and low-cost servo, where you can see the gearbox that acts as a reductor. This is an example of the motor that can be inside, and this is a schematic or a basic schematic of a servo like this. So basically you have a DC motor. This DC motor drives a gearbox that reduces the rotating speed of the motor. The output shaft will rotate at a certain speed, and there is a potentiometer that is attached to the output shaft and can measure the relative or angular position of the output shaft. And then you can control, and the easiest way to do that is through a simple PWM signal. You can control the final angle that you want to achieve with this servo motor. And of course, in this case, this is a very simple servo. The feedback loop just includes a potentiometer, which is not a very precise way of measuring the angle, but at least is very inexpensive. And the control is also very simple, since you can generate a pulse width modulation signal and by changing the time that the signal is on, you can change the output angle of the shaft. Since servo motors is so interesting as an actuator in robotics, normally we have to consider different sets of parameters according to the type of application that you want to acquire a servo for. You normally have to consider maximum available torque, which is available at the final axis, the angular velocity range, the maximum covered angle. Sometimes you can also use a servo as a free rotation system, the angular resolution that you can actually achieve, the gearbox materials. The gearbox material can be normally or either plastic or a metallic gear system. Of course, for low cost servos, this means that the gearbox will be in plastic, but for high quality servos, then you'll find metallic gearboxes. The type of control that you have to apply or use to control the servo, and also the dimension and weight of the servo itself according to the final application. Here you can see, for instance, a high-tech, very low-cost hobby servo. Down there you can see a much more expensive servo for small dimension robotic applications, a dynamical servo. This, for instance, can be used to control a mobile arm in a robot, and also there are very different instances of larger and much more weighted industrial servos for very large applications. In the case, for instance, of these dynamical servos, the control, instead of being done through the modulation of a pulse, is actually done sending digital multi-drop messages through a multi-drop bus, and this allows, among others, a precise control within some limits, of course, of the parameters, such, for instance, the end angle, the angular velocity that you want to use to reach that angle, and the maximum torque to be applied. The fact that you can also control the maximum torque means that you can use the dynamic mixel servo in a compliant mode. So the servo will apply the force, but if it exceeds the maximum torque that you program, it will stop. In this particular slide, you can see a combination of a mechanical setup together with two different actuating systems. And the resulting part is actually the system that is used within the Cambada soccer robots to shoot the ball. So this is the system that we call the kicker. You can look into here and see that it is composed by a solenoid. You can see the plunger that goes through inside this part. There is the coil outside that plunger, and here in the back this is an example of a servo. This servo is then mechanically connected to the front, so it can rotate around this pivot point, and it allows to move sideways this mechanical part that is used to kick the ball. Whenever you apply a current to the solenoid, it will generate a magnetic field that in turn generates a force that pulls the plunger towards this point. And by pushing this mechanical part, this is a kind of let's say a kind of a foot, it will kick the ball and generate a lob shot. I can show you how this works in practice. You can see that if we apply the current, this is what happens. So the plunger moves forward and then moves the kicking part that shoots the ball. The other actuating or actuator system that is used in this kicker is this part that you see in the back. We already referred to it. This is a small servo. This servo is, upon the application of a signal, is rotated in the direct direction, pushing this point. This point in turns is able to move this front kicking system to the side, and by moving it to the side it allow later on the plunger to move freely without touching this part. An example of that can be seen like this. So as you saw, there was a rotation in the servo part that pushes sideways the kicking part, as you can see here. Finally, with the setup in this position, if we apply a current to the solenoid, the plunger again will move forward, but now it won't touch this part. It will touch the ball directly, almost at the actuator level. And in this situation, instead of a lob shot, it will produce a kick that moves the ball on the floor. This kind of kick is used, for instance, for making a pass between two robots. You can see that by this sequence of images. As you can see, the plunger is free to move forward and it will kick the ball almost at the actuator. Of course, that the speed at which this plunger, the central plunger, will move it's dependent on the current that is provided to the coil, but also to the amount of time that that current is running on the coil. So it's proportional to the energy that is provided to the solenoid, and therefore by modulating that time we can also modulate the force that is applied to the ball, and so we can just make a very strong kick, or otherwise you can make a very slow kick depending on that particular level of energy. Apart from the solenoids, you can also find different types of electrical linear actuators that normally comprises a DC motor associated with a worm screw on which or from which the actuating element is moved. You can see here an example. The DC motor is over here, and then this will act by a set of gearboxes to a to a worm screw that will move that plunger in and out. And this is normally used to position with some precision a certain element within the robot or a robot arm, depending on the direction of rotation of the DC motor. So you can rotate clockwise or anti-clockwise. The actuating element, which is there, will also move outwards or inwards according to its current position. Normally there is the inclusion of a potentiometer or some sort of limit switches that will not allow this plunger to move farther than its possible limit or inner than its possible limits. In the case of linear actuators, normally is also very common to find actuators based on pneumatic or hydraulic energy. This is normally not used within mobile robots because this would imply that you have to store the energy within the robot itself, and the type of containers that it requires normally are heavy, bulky, and require the capacity to store very high pressures. But in any case, this is possibly other type of solutions whenever you require probably a faster movement of a linear actuator. To end up this class, we will just refer briefly other types of technologies that you can currently find and that can be used within mobile robotics. The first one are known as pneumatic artificial muscles. This is also known as air muscles and are based on the stretch and contraction of an elastic tube by varying the air pressure within the same tube. And contractions can raise up to 40% of the original dimension. You can see here exactly these black tubes, for instance, here and there, are examples of pneumatic artificial muscles. When you blow air or push air in these muscles, they will expand in this direction and contract in the opposite direction. So they work very much like our own muscles. Other type of muscles which are not so flexible as this one are called wire muscles. They are based on a compound, known as nitinol or sometimes flexinol. And this type of string, because this is like a wire, can shrink up to 5% of its length. So it's not much, but for some type of applications, this is a very interesting approach. Of course, in this case, we are actually using electricity as primary energy, and the way we produce the shrinking of this material is by subjecting it to an electric current. This can be used in particular in very small dimension applications. A third type of other actuators are electroactive polymers. These are based on plastic materials and can expand substantially due to an electrical signal applied. So instead of being a metal, this is actually a material based on a plastic that can change its dimensions based on an electrical signal applied. This type of actuators have a serious limitation because they are not able to support large mechanical loads. So they can be used for very light robotic applications, but cannot be used to situations where the load is significant. Finally, and going into micro robotics, let's say, we should also refer piezoelectric motors. These are used in micro and nano robotics. Nano robotics meaning that the robots themselves are something that measure totally something within the dimension of microns and can be put inside the body of a person, for instance, and navigate the body to deliver, for instance, a little bit of medicine inside an eye, for example. And this type of piezoelectric motors use the piezoelectric principle. And the piezoelectric principle states that there are certain types of crystals that, when subject to the application of a voltage to two opponent faces, will produce a compression force in the faces that are normal to these ones. These generally are used to generate mechanical vibrations in the order of tens of kilowatts, which can then be transformed into the rotational or linear motion. These piezoelectric motors can be easily adapted to really small moving robots. In this last slide, you can see the video of a very small hexapod based on the electroactive polymers. And as you can see, actually this is, exactly, you can see each leg will distort and move when acted upon with an electrical signal, and this will allow them to move as a small spider, let's say. And as you can see, this is a very small and light robot, but is a good example to demonstrate this type of technology when applied to mobile robotics. And that's all for today, and see you next class.